Today, we are going to talk about liquid propellants. Let's quickly review all of the propellants. In a solid propellant, you have the fuel and the oxidizer mixed together into a solid that is packed into a container. In a liquid propellant, you have the fuel and the oxidizer, which are kept separate from each other in different containers, and then they're mixed together in the combustion chamber. In a hybrid propellant, you have solid fuel and liquid oxidizer, which are once again kept apart from each other, and they're mixed together in the combustion chamber. And then the plasma or ion thrusters are totally different from these types of things. They don't use chemistry at all. So let's talk about liquid-fueled rockets. In a liquid-fueled rocket, you have liquid fuel and liquid oxidizer that are then combined in a combustion chamber to once again make this exothermic chemical reaction, which basically results in this super hot gas. And then that super hot gas is converted from temperature into bulk motion in the nozzle. The nozzle has to be super light because you don't want to add a huge amount of mass onto the rocket, but you also want to make it so it doesn't melt. So the nozzle itself needs to be kept cool, and that's one of the things that we'll talk about today. The liquid propellant rockets were first flown by Robert Goddard back in the early 1900s. Liquid fuel and oxidizer are mixed together and they're stored in separate tanks. Most common oxidizer is liquid oxygen, which has to be kept very, very cold. Both the liquid fuel and the oxidizer are pumped into the engine's combustion chamber. So you need to have pumps which move the liquids. So the pumps allow you to control the mass flow rate in the rocket. So you can throttle down the engines, or you can throttle up the engines, or you could turn off the engines and then turn them back on at a later time. You can have exhaust velocities, which are 3,000 to 4,800 meters per second, and that depends on the fuel, as we've talked about in the past. Solid propellants, on the other hand, have an exhaust velocity, which is around 2,500 to 3,500 meters per second, so somewhat less than the liquid propellants. We use liquid propellants to get us off the ground, to get us into orbit. They're the most common type of fuel that are used today. They take most of the things to orbit. So Falcon 9 uses liquid propellants. Delta IV uses liquid propellants. Electron rockets use liquid propellants. The Ariane 5 and the Soyuz use liquid propellants. And the Space Shuttle main engine actually uses liquid propellants. So a lot of different things use liquid propellants. You can also use liquid propellants once you get to orbit. And so a lot of satellites and orbiting vehicles like the International Space Station or the Space Shuttle or any type of satellite has what's called thrusters on them. And those thrusters allow you to maneuver in space. So you can do things like putting delta V on for doing Hohmann transfers and stuff like that, or you can actually control the attitude of the shuttle, like what is shown here. You can actually use these to cause rotations around the center of mass. There are a lot of benefits to liquid propellants. So they have a much higher exhaust velocity than solid propellants, as we just talked about. You can throttle the engines. So if you decide that you want to reduce the thrust, you could just simply slow down the engines and that reduces the amount of thrust. Or if you want more thrust, you can just throttle up the engines, which is really fantastic. It allows you a lot more control. You can restart the engines after they've been turned off. So you can get up into space, you can do some stuff, and then you can turn back on the engines and do more stuff. You can adjust the orbit after initial insertion. So say you want to go to 500 kilometers altitude, but initially, you only got up to 490 kilometers because, some of the calculations were off or something happened where, you only got up to 490. Well, if you really want it to be at 500, so you can turn those engines back on and you can boost yourself up to 400 or 500 kilometers altitude. So you can adjust things. With a solid rocket, you can't do any of those adjustments at all. Then one of the things that Falcon 9s have been doing, or SpaceX has been doing, is you can re-land the first stage. So, the first stage goes up, it lets go of the second stage, it has turned off its engines and everything, and then it turns around and it thrusts a little bit to deorbit a little bit, to control itself down into the atmosphere. And then it turns off and it waits for a while, and then maybe it adjusts its flight path a little bit. And then as it gets close to the ground, it reignites those engines, and then it burns, and then it slows itself down as it gets to land. There are a lot of weaknesses of liquid propellants also. There is a lot of really, really complicated plumbing and pumping that has to happen. If one part fails in this plumbing or this pumping system, the whole system can fail. Liquid oxygen and liquid hydrogen must be stored at very, very cold temperatures, and so that makes it a lot more complicated too. You have to deal with things like ice formation and stuff. You have to insulate things, which adds a lot more mass. The tank system needs to account for the liquids. So the liquids, are not like solids. They don't just stay where you want them to. They can move around. And so as the rocket is going up, these liquids could slosh from side to side. And you can imagine that it could cause the rocket to veer one way or the other way. It can change the center of gravity. It can do all sorts of things. So you have to take into account all of that sloshing, and you have to design your storage tanks to minimize the sloshing. And then some fuels and oxidizers can be pretty bad for humans, and leaks of those really bad fuels can actually be fatal to humans, so you want to watch out for that. Some of the best exhaust velocity fuels are not used very often because they're really bad for humans, and so we shy away from using those things. Let's talk about nozzles and cooling of nozzles. Rockets need to be as light as physically possible because every kilogram that you put to your rocket means you need a lot more fuel. But the nozzle shouldn't melt. Well, luckily, we have this really, really, really cold stuff. We have this liquid oxygen that's flowing through the system, and it's at like minus 180 degrees C. And we can use that to actually cool down our nozzle. So what we can do is we can have plumbing which goes around the nozzle, and we can have our liquid oxygen come through that plumbing, and that keeps the nozzle cold, which takes advantage then of like this very, very, very cold liquid oxygen. Fuel injectors. If you have a liquid oxidizer and a liquid fuel, you need to mix those together, just like in a car. This is much more complicated than in a car, though, because in a car, you actually are just burning just a tiny, tiny amount of fuel. But in a rocket engine, you're burning a huge amount of fuel, and you need to have it really, really, really well mixed. It's easy to mix fuel and oxidizer in a very small area than in a giant area. So you need to have very different type of fuel injectors for these very large engines. So this is showing you a combustion chamber, a fuel injector for the Saturn V. And you can see lots and lots and lots of little itty bitty holes where the fuel and the oxidizer come out and they mix together. So in summary, liquid propellant engines have several advantages and disadvantages. There are many advantages. They are higher exhaust velocity than solid propellants. You can throttle the engines up and throttle them down to control the thrust, and you can restart the engine, which allows you to control the final altitude of your orbit, or you can re-land the first stage of your rocket if you want. The disadvantages are they're very, very, very complicated. They have lots of tanks and plumbing. You can take a long time to actually fuel. You know, when you decide that you want to have a launch, you have to put all of that liquid oxygen and liquid hydrogen into the fuel, and it can't just sit there for a long time because it's super, super, super cold, and you need to keep it super cold. And so if you abort your launch or something like that, then you need to drain those and put it back into the storage tanks to keep it cold. So that adds a lot of complexity to the system. And leaks can be very, very, very bad for people. They're mainly used for rockets that go to orbit and on satellites' thrusters. And they're the main fuel that is actually used in rocketry today to get to orbit.